Welcome to the Cosmic Pie Podcast, episode 33, year number 3.
Woo.
I am your host, Wayne Barkhouse.
And I'm Robert Moore.
We're broadcasting live on the campus of the University of North Dakota here in cold a little bit, Grand Forks.
Just a smidge.
A little bit of a change
really
in
bad.
temperature from last week. And we'll talk about that a little bit later, maybe.
Yep.
As a disclaimer, Robert?
Okay, the opinions expressed in the show are those of myself, Wayne, and our guest, not those of the University of North Dakota, the Department of Physics and Astrophysics, the College of Arts and Sciences, or anybody else. Come at us.
Yeah.
We're it.
And unlike the federal government, we're open.
We're open.
We're open for business. So if you have any comments or questions you'd like to send to us, please use that chat feature, and we'll keep an eye on that. And also, don't forget, for those who like to go to Spotify and enjoy your pods, we do upload the next day on Spotify, so that is also available. But today, let's start this off right. We have a very special guest, a new professor to our department here at UND, teaching assistant professor. We'll let him introduce more of who he is and where he comes from and his background and all of that. So please welcome
Professor Jaad Tannous.
Jaad Tannous. How's it going, folks?
Okay.
Thanks for having me.
Quite welcome. Glad you decided and joined us, yeah.
Well, hey, I saw the invite. I was like, really? Me? All right, that's good.
You now are world famous. You realize that. Everything you said and will be able to get you in the court of public opinion. So let's start off, first of all, a little bit about your background, like maybe where you grew up, why you became interested in science and physics in general.
Yeah, so I was originally born in Rochester, New York. Spent a good 6 years there. So did like first grade. Was always interested in science. Gifts were always, things about the globe, books on the solar system and all that stuff. Then due to some family issues, we moved back to Lebanon. So my family is originally Lebanese. And that's where I spent the remainder of my childhood. Throughout middle school and high school, I was always adept at chemistry and physics and mathematics. And that stuck with me. And I became interested a lot in avionics and aviation. So I figured, you know what, like when I started applying for university, it was always engineering in the back of my mind, especially aeronautical or aerospace. But when I got into high school, and so in the baccalaureate system back home, we tend to take more science than we do here in the States. So we got introduced to a bit of radioactivity, beta decays, a bit of more physics, intro differential equation stuff. And it sort of stuck with me, and my interest never wavered in physics itself. So come freshman year or sophomore year, we skip a year at Beirut because our baccalaureate system accounts for the freshman classes. So if you look at my undergraduate transcripts, all the 100 level classes are passed. So that was a nice thing. So at sophomore year, I was able to I got accepted as a physics major because there was so much pressure on the engineering school that I applied to both and I got into the physics program. But because, in the Middle East and Central Asia, you're either an engineer, a lawyer, or a disappointment. So everybody applies to engineering.
I hate that.
So I got accepted into the physics program. And now when we came into the junior level, I sat in the engineering courses, and quite frankly, quite honestly, I was a bit bored. And so in the physics classes, I was at the edge of my seat. We're probing problems, studying Lagrangian mechanics and Hamiltonians, and diving into the quantum world. And when I sat in the engineering classes, was bored. No offense to your engineering audience, everything was tabulated. Probably had a few bad lectures and professors. Oh, it's all tabulated. You don't need to think about it. Well, don't need to think about it. That's sort of a problem for me. So I dropped the notion, and here we are.
Okay.
So I graduated with my bachelor's in physics from the American University in Beirut. And then I applied to the master's program there. And from there, I applied to the Ph.D program at Clemson in South Carolina. Go Tigers. And, now I should probably say go Hawks, but I don't want to anger both. Well, hey, go both. They never meet on the football.
Fighting Hawks.
Yeah. Yeah, my interest in physics was always astronomical, astrophysical. So in the master's program, I wanted to get started in I wasn't sure if I wanted to do planetary or galactic. So my first advisor did both. There were some disagreements. Let's call them creative differences. And then I jumped ship to the other professor, Professor Munib, who did stellar evolution. So I got my master's there. I worked most of my master's there, but because of some personal reasons, I had to leave the program early and move to Clemson to start the PhD program before I defended. So then I defended it there, and then under Professor Bradley Meyer, I worked mostly on the nuclear physics part of certain capture processes we can get into later on, and that was the bulk of my PhD. So graduated last May, and here we are.
Cool.
Now, because you grew up and did a lot of your educational foundational work in Lebanon, was there any challenges like for the politics that was going on at the time?
So in terms of the only challenge as we saw was that we never got exposed to conferences in Europe or the U.S. where obviously most students would require a visa or travel funds were a bit strained. The government really didn't affect the education much. The only thing that if the government wasn't functioning, our baccalaureate exams were exempt. So you didn't have to sit for a week taking baccalaureate level exams and see if we passed or not. It was an automatic pass. So if the government was shut down, it was kind of good for us.
Right.
I wasn't so lucky, but my sister was.
Right. So what about exposure like to physics related things? And I'm thinking in terms of were there any observatories on campus and things of that nature?
The American University of Beirut does have one of the first observatories in the region. However, during the war, that got shut down. The telescopic components were confiscated, and then when the city rebuilt, so much light pollution surrounding the observatory, it just sort of became a empty space. So they converted it into a museum at the time. There was another university that recently, at least if my memory isn't as faulty as it should be, last decade, the Notre Dame University, nothing to do with the Illinois one. They opened one in their main branch that sort of is because where the university is situated is between two valleys, and the cities are behind it. So if you're observing towards the Mediterranean, there's less light pollution, and they can make observations. And the professor started an astronomy program there, I believe, and it's flourishing as far as I know.
Oh, nice. You don't have to worry about like we do in January trying to go out and use a telescope when it could be like minus 30 Fahrenheit.
I'm looking forward to that.
Ears are frozen in place, and
That's
cloudy
right.
as all can be. And
Yeah.
You need special grease on your mount for the telescope in order for it to even move, the function.
Which
right?
I found out the Space Studies Observatory does use that low temperature grease. So
Yeah.
I was hoping they did.
Well, we have telescopes in Antarctica,
Right.
so clearly there's a way of making them work in an extreme cold environment.
Yep.
So,
good thing grease is color coded too.
yeah. Just don't taste it, right?
It's not flavor coded, folks.
It's not like
Just
Tide
color
Pods.
coded.
Well, people eat Tide Pods, right? So you never know what they'll do with grease, right?
Oh, Lord.
Now, when you think about the astrophysics stuff that you were doing for your PhD, can we dig in that a little deeper? Like what specifically were you looking at and what issues were you trying to solve?
So the bulk of my PhD work was the focus on how nuclear structure can affect pathways taken during S-process nucleosynthesis, where the S process stands for the slow neutron capture. So basically, stars can't make anything heavier than iron in its core because the temperature requirement to fuse iron and keep going is much higher than the hottest temperatures we've predicted to see within stellar interiors themselves. So a paper by Boyle, and the B squared FH paper.
Right, yeah.
Blanking on the name here, sorry.
Yeah.
So they basically laid out the work on how various capture processes will take us heavier from the iron elements into the actinides, the lanthanides, the radioactive materials. But even each process has its own limit. So because the S process is relatively slow, you can have neutron captures that have of the order of days to years, versus beta decays happening on the order of seconds. So between one neutron capture and the next, if you reach a beta unstable isotope, that will preferentially decay, and then you'll reach up to you'll climb the isotopic chart, and excuse me, but the S process specifically has a termination limit. So because of, and it reaches the what's known as the the lead bismuth polonium loop. So polonium is an alpha decayer, bismuth beta decays back, so it all circles back down to lead. Now, because the temperature and the neutron flux range during this process is low enough, you cannot exceed the beta decay and the alpha decay rates of those three isotopes. So you'll sort of like circling the drain, where you'll terminate in that loop. And various processes can get you up to that loop. And my study was to focus on how nucleus structure can affect a particular loop surrounding krypton 85, and how it affects the isotopes of strontium and rubidium.
Right. So you mentioned that the one paper, so that's the historic paper. That's the one by Jeff and Margaret Burbidge and Fowler and Hoyle.
Yes.
Right.
Yeah. Always it gets me tongue-tied.
And Hoyle is interesting because he's the one that supported the steady state model of the universe.
Right.
And actually came up with the term Big Bang as a negative comment about, so there's a lot of history there, obviously. So when you talk about the slow neutron capture, so we know, for example, in supernovae explosions, whether they're type 1a or the core collapse supernova, that you can form a lot of those heavier elements beyond iron because you have that energy available in a very rich environment of neutrons. But that's like a fast neutron capture type of process.
Yeah, so the major difference would be, because you have such a higher temperature and higher neutron flux, you can ride the chain of unstable isotopes farther out before you reach a beta unstable isotope that takes you back into stability. So you can think about it as a longer treadmill step going up.
Simply because beta, to me, it's always seemed like you've got a high enough neutron flux that that 1 second beta decay rate that you were talking about, that you mentioned, you're getting another neutron. Yeah, you're getting another neutron hitting before that happens.
Right. So it's always a competition of what's more likely to happen. Is my structural instability going to happen first, or I'll be smacked in the face with another neutron?
Right.
Right.
I like that phrasing. He's smacked in the face.
You know, it was interesting just a couple of years ago, and I'm sure you remember this, when from the LIGO observations of gravitational wave detection, that there was more emphasis placed on the fact that when you see two neutron stars that merge together, that actually can populate, the rest of the periodic table beyond normal, stellar evolution type processes. And it was one of those things that I never really thought of when I was first learning this thing. In some ways, we are told, well, those higher elements like gold, who doesn't want gold, right? You see the price of gold? It's like $4,000 an ounce now.
Right.
Oh yeah.
I remember it when it was like 200.
And people flipped out when it was
$200 back then.
Yeah, exactly. To me, it was $4,000. But anyways, to form gold, all these exotic things, that we love, it really was the supernova explosion. But now that seems not to be the case. There's a lot of controversy, or at least new research that indicates that maybe it is these merging of neutron stars that's creating a lot of the gold, for example.
Yeah, so the site where the rapid process happens has been it's always been in flux, because if you look out at the solar system abundances, or if you look at the galactic ones, if you statistically try to populate like how many supernovae would have had to occur for our process to create all these elements, we see there's a bit of a dip, so we need more potential sites for it to happen. And the neutron star merger was one of them, and it seems that can make up for the gap. But now with gravitational wave detection, now we can see, okay, how many have actually happened in the universe, and maybe that should make up the difference.
Right.
Yeah.
Okay. That's cool. Now, when you talk about slow process, what are some of the sort of common phenomena that would be responsible for those type of events to occur?
Right. So typically in slow neutron capture, so there are two main sites for it, and they happen in all the stars, but for each mass range, they happen in different phases. And so the main slow neutron capture process happens in low to intermediate mass star during the late stage evolution of the star. So the common stellar evolution stopgaps are depending on what's going on in the core of the star. So the main sequence, for example, is when the star is burning hydrogen into helium. Then you have the helium burning phase, which then the star turns into a red giant, is burning helium in its core into carbon and oxygen. And then whether or not the star is big enough to fuse that carbon and oxygen into neon, magnesium, and keep going. So if it stops at oxygen, carbon, oxygen, or oxygen, neon, magnesium, those are intermediate mass stars. The lower mass stars, like our sun, for example, will end up with only a carbon-oxygen core in. But so towards that end, you will end what will happen in the stellar interiors was known as a pulsing phase or thermal pulsing phase, where you'll still have temperatures high enough in the stellar shells that you can still fuse helium into carbon periodically. And that's why they call them thermal flashes, because the star periodically puffs up, brightens up a little bit, and then relaxes back down. And throughout this periodic period, the carbon that fluctuates, well, the convective envelope mixes in hydrogen down, then through a couple of capture processes, you'll end up with carbon-13. And that carbon-13 will act as a neutron source, and the neutrons there throughout that process will capture onto any existing iron that was captured during the star's collapse, and then that kickstarts the S process, where then you start capturing along isotopic chains. The first beta unstable iron isotope, which I should know this by now, iron 50, is between iron 59, iron 60, and then that beta decays into cobalt, then nickel, then all that good stuff, and then the chain starts repeating itself. So that's where most of the S process happens, late stage evolution of low mass and intermediate mass stars. Now for more massive stars, somewhere in the vicinity of 12 solar masses and higher, you can get S process in the outer envelope that surrounds the helium core that is burning. And then now, because these massive stars are more short-lived than than the lower mass counterparts, the S process itself doesn't survive long enough, because the star itself doesn't survive as long enough to produce as much or to get as far in the S process chain as it will for its main branch counterparts. So in lower mass stars, the S process will reach the lead, bismuth, polonium loop that we talked about. In massive stars, depending on the mass and the composition and all that good stuff, where it terminates depends. So the stop point is relative to the star itself in the massive phase, but for the main branch, you will get up to those heavier stuff.
Okay, just for sake of explanation, so you, in general, for those who don't really know this material very well, you can think as a dividing line between low mass stars like our sun and high mass stars that ultimately will go supernova, core collapse, as around 8 solar masses when they're on the main sequence, approximately.
Well, I have an issue with that number.
We can tell.
Yeah.
There's a reason behind it, because you see an 8, 9, and a 10 solar mass star, they will evolve into what's known as a super AGB star, where they will burn the carbon oxygen in their own cores and form oxygen neon cores themselves, and then the S process. So you get a secondary thermal phase with the new core. So I know why they classify more massive stars as 8 is because if they are in a binary, then they can go type 1 or type 2 supernovae, depending on what they absorb from their binaries. But you see, if you evolve an 8 solar mass or a 9 solar mass star on its own, it will never go supernova. You'll get an oxygen neon magnesium white dwarf at the end, and that's it. So if the end result of a singular evolution is a white dwarf, how can you call it a massive star? Versus a massive star at the end of its evolution will always go nova or core collapse if it's heavy enough, and you'll get your black hole at the end.
So what's that mass then that you would say a single star, when it's on the
Well,
main sequence to go core collapse supernova, what would that mass have to exceed?
so depending on rotation rates and composition, from the papers that I've seen at least, estimated cutoffs have been between 11.2 and 11.4 solar.
Okay.
But depending on rotation and composition, that can bring it up to the 12 limit.
Right.
But 12 is guaranteed to always
Pop.
behave a certain way.
Yeah.
Okay.
So
Now, when a star like our sun in the future, distant future, undergoes the S process, when through the helium thermal pulses, is that elements that are created in that sort of environment, do they reach to the outer atmosphere so they would be observable using spectra, or do they
Yes.
maintain down inside where it's very difficult to see?
that's an excellent question. So one of the indicators of the formation or the S process was the detection of technetium in an advanced star. Again, I'm sorry I'm blanking on the names here. I wish I wrote them down. So basically, the detection of technetium, which has no stable isotopes on the stellar surface, indicates that, first of all, proof of the S process actually happening. And the second is the importance of convective mixing. So I like to think about convection in a star as scooping ice cream from a bucket. Because if you scoop an ice cream slow enough in the bucket, what happens is the top layer circulates in the scoop and becomes on the bottom, and then the bottom becomes on the top. So the way I think about convection is that it scoops down, the convective zone scoops down into the core mixing material all the way. It finds what's happening in the convective and the S process zones, scooping them back up, mixing them to the surface, and circulating the material that way. So kind of like how when you're scooping ice cream, what's on beneath the scoop, if it rolls perfectly, what was below becomes on top, and what's on top becomes on below. So that's how I like to visualize it.
Right.
Yeah, because you can think of the dredge up process, right?
Right. Yeah.
Right.
Yeah. Okay. And that makes it observable because a lot of people don't realize they think you can somehow probe the interior of a star all the way down to its core by looking at a spectrum, but that only depends what elements, atoms get to the outer atmosphere.
Right.
And that makes an impact or an imprint on the spectrum that we observe.
And for instance, if I'm remembering my stellar evolution class correctly, our sun is not convective throughout. It's actually got a radiative core that doesn't convect, and then a convective envelope. So,
Which is
That convective envelope only mixes material from the envelopes outside the core back to the surface.
right.
right, and that just depends on how rapidly the temperature changes as distance from the center. So the
Right.
temperature gradient will give rise to either radiative zone or the convective zone.
Whether the adiabatic gradient is greater than the radiative gradient.
Whether things
yeah.
are thermally stable or not.
Well, when you even talk about like low mass stars, they're convective all the way down.
through. That's part of why they have lifetimes on the order of trillions of years instead of mere
Well, that
billions.
can also be attributed to nuclear processes, right? So
Right.
you evolve as fast as your slowest reaction.
Very
So
true.
If your
Yes.
slowest reaction is the very first proton capture, then you're going to live for a very long time.
Now we think of the Gaia mission and others that we've had. They can, in some sense, the main diagram of stellar evolution or stellar physics is the Hertzsprung-Russell diagram.
Right.
And people always like to look at that and compare that to what we've had in the past based on observations and even modeling processes, of course. And so with these new spacecraft that do more precise measurements like Gaia, then we can get a better, one would think, observer's HR diagram. And even in an observer's HR diagram, different regions of that diagram, like the main sequence, for example, so this is where our sun currently is, happily converting, hydrogen to helium in its core. And those regions, have a finite spread to them. They're not like a single line or curve,
Right.
right? And that spread is very useful because doesn't that tell us information about what's going on with the star in terms of maybe its composition, so metallicity, whether, like you mentioned already, angular momentum type of things, and maybe even magnetic fields all have an impact on where a star actually would be in a plot like that at any given moment in its history, right?
So actually, I've done, so part of my master's thesis was modifying an existing stellar evolution code to take into account rotation and angular momentum distribution throughout the star, how it affects mixing and whatnot. So if you look at the structure equations, so you can think about the star as always the competition between pressure, thermal, and radiation versus gravity pulling it in, pressure puffing it out. So if things are going in a circle, if you remember for our audience that remembers their initial or introductory classical mechanics, if you throw something in a centrifuge, the centrifugal force or the effect will try to pull things out. So you require less pressure to even counteract gravity, because if you're going in a circle, the balance shifts. So that translates throughout the whole star, and the pressure requirement changes, therefore the temperature requirement changes. Stellar cores live longer, the HR diagram shifts, the luminosity gets affected. You have more mixing processes, so your composition throughout the star will shift. So now your convective stability also changes, the extent changes.
Oh, wow,
It
yeah.
becomes, I know as professors, when we're describing things simply for our students, it's 2-point interactions, but then you extend it a little bit and you have things go on inside and everything couples to everything. And so, but yeah, even just before even adding magnetic lift or magnetic fields, just by adding rotation alone, which is the first step in doing that, you automatically see the shift within the same star. And you can compare if a star is, let's say, fast rotating versus slow rotating, how much will it be affected? Our sun is considered roughly a slow rotating, so a static model works well enough. But yeah, for those fast rotators, you can get, that's why, like you said, Wayne, that's why you get like a band within the HR diagram and not everything falls into single file. So that's one of the main reasons.
Yeah, and you could sort of compare if you want several binary systems, so two stars in orbit around each other. One are fast rotators and some are slow rotators, and look at the difference in terms of their expected evolution.
Right.
And that would definitely separate the two, right? And
Even if they're the same class, they may evolve. That's the
yeah.
word. Differently.
I mean, we always tried to present things, like the old joke in physics, right? Assume an elephant's a sphere type of thing. And we like to do that for our students, but in some sense, you can't start off, obviously, and teaching them the complexity because you get lost right away in the details. So you got to start simple and build up. At least that's how most people learn.
Yeah.
And that way.
I kept brushing up against that doing my master's because we started out learning about local hydrostatic equilibrium, as to model the solar atmosphere. And I was like, but it breathes every 6 minutes. There is no local thermodynamic equilibrium here, hydrostatic equilibrium.
Well, right. Well, that's the point that I wish that maybe things would be emphasized more, is that time scales are relative, right? So as far as the age of the star is concerned, yeah, it can be counted as equilibrium. It's not shifting. Obviously, even within the hydrostatic equilibrium, right, the radius shifts back and forth during different mixing processes and thermal processes. But if they evolve over the term of the century, if the star lives for billions of years, it's not even the time it takes for it to blink,
Right.
So in relative terms, it's equilibrium. Now, if you want it to be numerically more involved, you put down the acceleration term and it'll shift things a little bit. But,
Right. And that's what I ended up being told, that along with we have to start somewhere.
That's definitely true.
And the other thing, too, I always find is like there seems to be a lack of detailed modeling. Detailed modeling here means accurate, as far as we could tell, based on our data, of the late stages in the evolutions of almost every star. Is that really true still?
Well, it's kind of hard to model something you can't see.
Right.
So, the beauty about what's been done by Chandrasekhar, Eddington, mixing length theories for convection and all that stuff, the groundwork that they laid down and the accuracy to which their approximations work is phenomenal in itself. But if you want, first of all, doing the simulations themselves, even back then and today, if you wanted to apply fluid dynamic treatment, simulations take forever to run. So that's why we stick to our approximations. But that's not to say that progress isn't being made to do 3D simulations and incorporate fluid simulations. So coming up with approximations that match what we can see observationally. First of all, the fact that they work at all is phenomenal. The second is it's, like I said, it's pretty hard to model what you can't see. So if you can't probe into what's going on into a star, how can you model a structure? So you have to sort of uh, use your intuition, try to model with what we already know. So if we know how lava lamps work, we can try to approximate that to a star, do all that and see how much things change. So I've seen a lot of convection simulations where they have get like cyclone effects. You see blobs moving all over the place, and like, that's. I mean, if you think about it like a big lava lamp, that's exactly what you would expect. But those simulations take forever to run. But then, again, what are you trying to simulate? Do you want to run the stars start to finish, and you just want to gloss over the nitty-bitty detail versus, for example, if you have dynamical instabilities versus sorry, blanking on the names again. So depending on the type of instability, do you really want to pause the simulation, go over a million timestamps for an instability that you can average over, or do you just want to sort of breeze through it and then look at the late stage?
And
So-
the other thing I assume you have to watch out for too is you can run, different simulations, you change various parameters. We always joke like, people who do numerical physics or computational physics have it made. They just adjust one parameter and there's another paper. This kind of thing, right? But as a joke, but what you really want to do though is you could run various simulations, but if they're degenerate in terms of observational ramification, observational parameters, then you're kind of stuck because you could have 10 different simulations that all give you the same gross sort of properties or macroscopic properties that you can measure with a telescope, let's say. But how do you know which one is the right one? You got to find something that kind of discriminates between them, and that seems to me to be extremely difficult.
Well, right. Well, you can simulate anything. So, but like you said, you need those observational constraints.
Yeah.
So, for example, if an HR diagram shifts one way or the other, well, why is it shifting? Is the star rotating? Okay, how fast? What's the composition like? Is it solar? Is it metal poor? Is it metal rich? Because your composition can also affect your luminosities and your temperature profile overall. Does it have star spots? How much of the how big are the star spots? Or do they eat half the observed surface area, or do they eat most of it? I mean, there are stars out there with star spots that are, they cover most of the observed surface area, and that temperature on that surface just takes a nosedive. So, I mean, yeah, you can simulate anything, but when it comes to matching it with observations, well, I know with an Avogadro's number of stars and galaxies out there, it becomes hard to mix and match. But you can at least say a classification of for stars that are rotating half their critical speed with this composition, their HR diagrams should look like this. You go to an observatory, you pick your favorite patch in the sky that has these solar masses, and you see how many of them fit, and then you can infer whether or not, okay, maybe these guys are rotating. Are they? Do they match? Fantastic. If not, okay, what's different? And then we can see.
Yeah, as an observational astronomer myself, one of the things I would look for is there anything new or novel that we could use to kind of constrain some of these models based on real observations. And maybe in the future you could think of things like, I don't know, like neutrino, right? So if you could measure somehow neutrinos coming from a star that's at the stage of
We
late
use
evolution.
spectroscopy to- Yeah, I'm sorry.
Yeah, I mean, something like that. Is there a way you could do that? Or you could think of gravitational wave physics gets so, accurate and we get really sensitive in way in the distant future. Is there something we could measure that way? You're always trying to think of something new,
Well,
right?
one of the major constraints where we use spectroscopy is so a lot of the nuclear reactions that we use in our codes, most of them are theoretical. So if we wanted to put a cap on them or to calibrate them properly, we use spectroscopic observations to figure out to see if they match. So we take a star that we know, preferably the sun, and we try to look at its output. So if the neutron flux is different, or if the output is not seen as we expect, we go back to the drawing board and we either tweak the rates or they get confirmed. So
Right.
We do use it. It's just, it's a big world out there.
Yeah. The other thing too is, isn't it true that even now people are still trying to measure as accurately as possible, like cross-sectional interactions of different atomic species and so on, to try to refine those sort of nuclear calculations that one would like to do?
Yeah, definitely, especially for neutron capture cross sections and their rates for processes like the R process and the S process, where the interactions need to be known. Now, I understand the frustration of experimentalists, because if your species decays in a few hours and you need 12 hours to set up the experiment, well, there's half your sample gone already. So I understand the frustration and the need for high power precision lasers and setting up the sample in good time. I was at FRIB a few years ago and just walking through their tours, and the structure required to chill the lasers and set up the samples, and the necessities to create samples and carry out the experiment in a time frame that's relevant to the system. Because otherwise, if half your sample is gone by the time you hit go, well.
Right. I was thrown a minor experiment on that very type of thing. I was working with magnesium MgO capsules, and all of a sudden we started having to worry about how quickly do they rehydrate after you dry them in the oven.
Yep.
And it turned out that it was quick enough that you can't worry about it. Right.
Yeah, that's interesting, because it seems like the low-hanging fruit obviously gets grabbed first. And then we're always left, this day and age of, number one, you could advance the computational and theoretical work to get into really exotic, really, very highly complex type of interactions. Or one could go back to the beginning and make sure, whether it's new measurements of cross-sectional reaction rates and so on, to make sure that we basically had it right early on, and refine that a little bit. And so, some people have the idea, I'm not saying we do, that a lot of the stellar astrophysics is done, right? It's a person's game that was over decades ago, that we should be spending our attention now on cosmology, looking at exotic type of objects that are far away, like AGNs and so on, or fast radio bursts, for example, or looking at things of really exotic type of stuff, like maybe stars, but now we're looking at merging objects or whatever, or some transient type of things that are there for a moment then gone again. What are they? And you really didn't notice them unless you had like a million of them to look at, and then you find the oddballs. This kind of type of astronomy, I guess, is where it's pushing now. But in some sense, depending on your feeling of the material itself and what you are interested in as a researcher, there's still probably a lot of work that needs to be done at the foundational level that maybe a lot of young researchers are not going into, because they get excited about other stuff they're exposed to, is what I'm getting
Flashy
at.
stuff gets first.
Yeah, exactly.
Who wants to dig through a 50,000 line code to figure out how to modify this thing?
Where's the bug?
It's not a bug, it's a feature. It works. Some files don't change.
We used to joke as graduate students, right, when someone would present a top or give a presentation on something related to like a computation or something, we'd always say, is it a 3D? Did you include magnetic fields? And what about the impact of dust?
Yeah. I mean, they're computationally expected. I mean, it's to me, it's astounding when Kippenhahn and Professor Mungaid and all of them were doing their computations on Fortran machines that took punch cards.
Right.
I mean,
Oh, Lord.
Just to think of the fact that they were the first ones to do it. B, the computational restriction of the thing need to churn and churn and churn and churn. In fact, they even had a budget for the printing paper, because they had to restrict how much the code had to output to make sure it was running right. And, processing speeds on those things, and how much they had to optimize it to get results within a week or a few days. Or it's astounding compared to today.
Within a week, I think you were right there.
Yeah, I mean, the jump itself is amazing. And now with support suite of doing things in parallel with GPUs and higher end CPUs today, using GPU parallelization to solve and invert big matrices, which effectively we have. I mean, most codes use 1,000 by 1,000, but still, if you can do it in parallel and keep things coupling or solving things simultaneously, for example, which is also another problem in stellar astrophysics, where you solve the structure equations first, then you solve the nuclear network second, and then if the two converge, you move on to the next step. When in reality, it all moves together in one nice flow. But if your structure equation is over a grid of, I don't know, 1,200 by 1,200, let's say, and you have how many nuclear reactions? 8,000, 5,000? How many we have known today? So immediately that's a 7,000 by 7,000 matrix. Good luck converting that and not running into problems and all that stuff. So, but with GPUs, that if you section it off and you use sparse techniques and all that, life becomes a bit easier. But if you can parallelize the whole thing and have it run simultaneously, and then simulations get corrected, you can include more physics now, becomes easier. And new mixing techniques, so for example, you can do magnetohydrodynamics instead of piecing in together, modifying the structural equations. You solve the full fluid equations if you can manage that. I'm pretty sure any hydrodynamicist in the chat is probably screaming at me right now, "You're nuts!" But if the technology is there and if there's a will, there's a way. If our forebears were able to do it with potato-powered machines, we should be able to figure it out today, or at least get the ball rolling. And coming up with proper mixing techniques. Because I know if you look at any stellar evolutionary book, whether it's printed today or earlier last century, they treat convection like a mixing diffusive process, which anybody that looks closely at the problem realizes that it's not the case. For the first order approximation, it works, but there's a difference between particles moving away like a random walk, or you spray perfume and it disperses, versus you have two blobs and they're moving in opposite direction, and the blobs are mixing inside themselves, and then they interact with other blobs and they mix and match and do whatever nuclear physics happens between them, and they exchange or merge, or they pop and deposit, reform. So describing that and have it run in sub-seconds for the next time step is pretty hard to do.
Yeah, I'm just thinking of the stereotypical professor who is accident prone, tripping over the steps of going into the computer science building with a briefcase full of punch cards, and they all fly everywhere.
Oh, yeah.
It happened.
I'm pretty sure it's happened.
It happened.
It's snowing or it's raining and they faded away. Then accounting firm gets involved saying, "Why are you spending so much money on punch cards?" Well, you see.
Well, you
I
see.
tripped.
It reminds like that. Do you have like a situation like the hanging Chad?
Those have happened too. Yes.
Did Gore win or Bush?
Yeah. I when I was taking Fortran in
Right.
college, my undergraduate, my grandmother was listening to me complaining about it all, and she started relating these stories of people tripping and dumping their cards or not punching them clean and
Yep.
all of these types of things. And she was
not
like,
having a 72 character limit is fantastic.
Right.
right. And so she was basically saying, "Stop complaining, you got it easy."
It reminds me of a funny story. So when I was working on my master's, when I was incorporating, I always had debugger lines, and I had the thing print just everything. So I make sure, no weird or random infinite numbers or zeros are not popping up where they shouldn't. And then my advisor walked in and he said, "What the hell are you doing? if this, back in our day, you would have ran through the printing quota." I looked him dead in the face and was like, "Sir, it's 2013, 2015. There's no printing quota. It's all on the computer screen."
Right.
Yeah, it's amazing how much things have changed. I mean, people like to say, "What would Einstein do today if you gave him a modern computer?"
Assuming he survives the cultural shock.
Assuming he didn't waste his time on the internet going to TikTok videos and YouTube. I didn't come up with anything.
How many Einsteins are doom scrolling?
I was too busy watching people do stupid stunts on the internet.
Or what would Newton do, or Legendre, or Gauss, or Weber, or Planck, or
Yeah.
Maxwell, or
I mean, there's a lot for that of dedicated, sort of non-distractive. I mean, wasn't Einstein the guy who picked, like, when he picked his shoes or socks or pants, they were identical.
Mm-hmm.
So he didn't have to waste time thinking about which one to put on.
He wore the same thing every day.
Yeah.
Yes.
No brain power is lost thinking about what to dress.
Probably. I mean, it'd be interesting if it were true.
No stress or
I
time
wouldn't
lost
know. I haven't
either.
heard that one.
Yeah, that's what they say.
But hey, you know, I mean,
yes.
Feynman had a good time before he got sick, and he got things
Right.
done.
Yeah,
Right.
that's true.
So,
But how many Feynmans are there, right? You know,
Well,
Yeah.
That's the
not
thing.
But
yeah.
you have to learn
To-
from everybody.
The other thing about Feynman, if he was doing what he did back then today, he'd be arrested
He'd be
or fired or
arrested.
something.
Yeah.
Yeah, so you gotta, yeah.
Who was, he left his own party to go watch the girls watch on the beach and
Yeah. Well, he would go to like campus bars and tell because he was young looking when he was assistant professor, and tell everybody he was just a regular student. They didn't know he was a professor until after, you know what I mean, right? The deed's
Well,
done. Then he would, by the way, I'm a professor here. What?
cultures change, things
Yes.
shift. I mean, wasn't Heisenberg a womanizer? He was actually having an affair with one of his other colleagues.
Well,
Yeah.
Schrodinger, right? Wasn't he the one?
that's the
Schrodinger,
one.
yeah.
Yeah.
Yeah, he was.
There you go. You know,
Yeah, he was doing a lot. And
busy in more ways than one.
well, back those days.
Sorry.
Yeah, well, back in those days, I don't know if he even knew about it. Maybe all that stuff comes out much later on in life
Right.
or something. But
Well, it was also, I've heard, correct me
Yeah.
if I'm wrong, but I mean, in the norm, you know, in Germany back then, or at least in Prussian era, you know, it was natural to have a mistress, and the mistress and the wife were friends. You know, how true that is, I've heard it. I don't know if it's true, but
I know
Yeah,
it
well, I've heard.
was reasonably true in an English
There
upper
you go.
upper crust scenarios, but
well, hey, most of the English physicists were lords themselves. So
right.
that's applicable.
So the rules didn't apply to a lot of them. So
and of course, Newton ignored all of that.
yeah,
It was only Newton. That was it. So
Well, I guess he got tired ripping off Raphson and Leibniz and
they just opened up a whole can of worms right there.
all righty then.
already starting. Everybody.
We'll get more viewers.
grabbing the sharp stick. Poop, poop.
Yeah. But yeah, so what are you been sort of working on lately? Maybe you can share with us some of the things.
So there were a few unfinished projects that I had started in my PhD. One of them is a Python package that I'm currently working on that can handle quantum level data. So we used it in our, I developed it as part of our paper that, so I'm blanking on the name. Brookhaven National Lab maintains the nuclear data structure files, and everybody has their own format on how to read them and manipulate them, and some are in C, some are in C++, people are trying it in Rust. And, well, I figured, well, why not just write a Python script where I can read any format. So the first format that I was able to read in was the structured data files, the evaluated nuclear structure data file, NSTEF for short. And then to work with Brad's nuclear network code, it needed to be output in XML structure. So one of the first things we were able to do was to cleanly read out the relevant nuclear data from the files, put it in memory, and then once it's in memory, we can run any of the calculations we wanted. So the Python code right now, it can do internal transition rates, it can calculate effective transition rates from unstable states that are loosely connected to the ground state, calculate the effective transition rate down that way. It can output to different formats. You can run calculations, you can evolve a species. So if I create a population of, let's say, aluminum-26 at a given temperature, and I randomly distribute the population over all of its excited levels, over time, if we hold the temperature constant or the temperature is a function of time, how will the ensembles of the different excited states interact, and where will things stabilize? So you can use the Python package to do that. What I'm adding right now is we want to use Hauser-Feshbach estimates to calculate transition rates from one species capturing onto another, so that way it's internal. And the reason why we chose to do it in Python was because whether you're running Mac, Windows, Linux, or whatever, you load it onto Python, it just runs. You don't need special compilers. You don't need to learn anything specific. And the way we had designed it, we kept it modular in mind, so that, and it's open source, so anybody can suggest, hey, this should be done that way instead of this way. And with new formats coming up, so they're currently, I think everybody in the nuclear physics community has complained about, we should update the structure that was developed in the 80s and is using the 80 character limit. So they're introducing a new format using the JSON structure. So I'm gonna, once they finalize theirs, I'm gonna incorporate it into mine. But yeah, and also I want to incorporate a graphical suite with it to that way you can get nuclear structure diagrams that you can find on NNDC. So if you want certain levels you're interested in, you can calculate missing transition rates. You can also use the tool, for example, to tell experimentalists where, hey, I need the transition rate from the 3rd excited state to the 5th excited state, because if we take out that rate, the transition rate the effective transition rate just takes a nosedive. So this is important, we need to measure it. So there are use cases for it. Other things I want to look at, I want to finish up that I started in my PhD, where we had started trying to classify the neutron exposure problem within the interior of stars. So Donald Clayton back in the day was able to characterize exponential-based neutron capture exposures. So neutron capture exposure tells you effectively how much neutrons are you exposed to at a given time step for a given temperature. And that has implications on the S process and the R process. Mm-hmm. And they were able to characterize exponential distributions based on solar system abundances back in the 60s and the 70s. The way we started was we wanted to, from the stellar interior, do things match up? Can we classify them? And I wanted to provide a tool that, if you use it in the way of a back of the envelope type calculation, can we get what the end the end isotopic abundances for a particular species when they were exposed with this distribution? So that way you don't need to run nuclear networks forever. You wouldn't require, if you're just interested in if I'm starting with I don't know, n abundances for a given species, at the end of the run, how much will I see at the surface? And you don't want to run through the whole stellar evolution thing. You can do a sort of back of the envelope type calculation that will give it to you. So I'm working on wrapping that up, just to name a few.
Right.
That sounds like a lot right there anyway.
Yeah, it's interesting.
Not that I'm complaining, but I think I already got the gist of how to handle students and balance teaching my credit load and trying to swindle research in a little bit, despite the fact that I'm contracted not to.
Yeah, it's interesting to note that an emeritus professor of ours from Department of Physics and Astrophysics, Bill Schwam, I don't know if you had a chance to interact with him much since you've been here. Yeah, so he has former student, Scott Crockett. Scott's from this local area, if I'm not mistaken. He works at Los Alamos National Laboratory, and he's done a lot of calculation, been involved in a lot of calculation, like equation of state under extreme pressures, and the rate reactions and all these kind of things. So maybe it'd be good to get Scott up here to give us, he's come once in a while to give us a talk, sort of what he's doing, the latest, greatest thing. So it would be great to have him up here, because I'm sure you two would have a lot to talk about.
Yeah, we probably had the same collaborators, because the Krypton 85 stuff that I did was with collaborators with Los Alamos.
Okay, cool.
Okay.
Yeah, Matt Mumpower, Chris Fire, and Wendell Mish.
Yeah.
In fact, drop a few names.
Right. In fact, we could have Scott on the podcast sometime and talk about some of the work
that's what I was thinking.
He was involved. He's been involved in and is involved in. So yeah, really interesting. Is there any slides of any of the work you want to show us to give us?
Yeah, I mean, I can.
Just to give some illustrative
about some of the things.
Food for thought for people.
Yeah, sure. So I guess I can share my whole screen and see what happens. So yeah, let's.
There we go.
Go into presentation mode here.
Uh-oh.
Was it F5? There you go.
There we
So I guess I'll just use this image.
Okay, we got part of it.
Do you not see the whole thing?
Not seeing the whole thing.
It's cut off on the bottom and on the right a bit.
cut off on the bottom and on the right. Well, hang on a moment.
Okay.
Technical difficulties. Let's see. Well, I
Would-
can just.
It wouldn't be a Cosmic Pie podcast without some technical difficulties.
I'm sorry, folks. So, is this better?
Now,
There we go.
That looks good because we can see the whole thing there.
Yeah.
The way that's displayed.
I mean, we see all of your.
Well, there's nothing
Yeah.
on the background, but hang on. Let's try. Third time's the charm, folks. Just share this. Better?
That's better.
Yeah.
Okay. So, yeah, go ahead.
I was just going to say, so we have temperature on the bottom axis,
Yes. So,
increasing to the right.
yeah, so on
Okay.
the bottom axis, we have temperature. So typically in astrophysics, you can tell who you're talking to by how they define temperature. If the focus is in nuclear structure, typically temperature would be discussed in electron volts.
Mm-hmm.
If you're talking to somebody that does stellar evolution, it's always normalized to billions of Kelvin. So that's why it's T9. So every unit of T9 is 1 billion Kelvin.
Right.
Okay.
And on the vertical axis, we have the neutron number density, which is how many neutrons do you have per unit volume.
Okay.
So the two red lines, and so, excuse me. So first of all, the T halves here on the top are, oh, I'm going to get rid of that. Oops, wrong thing. Sorry. So here we're trying to compare at a certain grid point, what would happen to Krypton 85? So Krypton 85 admits a stable excited state that has a half-life of 4.5 hours, and the ground state beta decays in only 10.7 years. So for the S process, how you get up to strontium 88, it gets branched. So typically, and can I annotate? All right, so most S process happens in this bracket here, where you have a relatively low neutron number density and the temperature ranges from about 0.2 billion Kelvin to about 0.48 billions of Kelvin. Now, the vertical line here is the equilibration rate of Krypton 85. So what happens, so Krypton 84 neutron captures into Krypton 85. Because of the angular momentum difference, you actually form more Krypton 85 in the isomeric state that has a total angular momentum of 0 versus the ground state that is 9/2. So just from basic quantum mechanics and adding angular momentum, preferentially you'll always get Krypton 85 in its metastable state. So what we are trying to do here is to gauge, well, what happens in the nuclear network for different astrophysical considerations. So like I said, for the S process, we are in the lower two quadrants. Now the vertical line is what is the required neutron number density required so that the capture rate on Krypton 85 goes from the ground state to Krypton 86. The vertical line tells me what the temperature rate is for Krypton 85 in the metastable to decay down to the ground state versus it itself beta decaying into rubidium 85. And this is what's creating the branching. So what we were able to work out was that for typical S process, so here typically low mass and intermediate mass stars are in this quadrant, and massive stars tend to be here. In this quadrant up top, you can have late stage for massive stars. So if you're doing carbon burning or doing shell burning S process, you are here. So the idea here is that we sort of created a cutoff of when is it important to include the isomeric state in your nuclear network and when not to, because adding rows and matrices to your nuclear network just makes it longer and harder to solve for. So for example, in the case of Krypton 85, if your operating temperature is above 0.3 billion of Kelvin, then you probably don't need to include it separately in your network, because it'll always decay down to the ground state, and then the ground state will either neutron capture if the flux is high enough, or the ground state itself will beta decay into rubidium-85. For intermediate mass stars, since the temperature is low enough, krypton-85, if it's produced in the metastable state, will remain in its metastable state and decay in 4.5 hours. And if it's produced in the ground state will itself decay in about 11 years. So what that means is that you will reach strontium-88 faster than you would, including the isomer, than you would if you didn't.
Okay.
So that shifts the abundances upwards, especially for rubidium-87, which is a notable cosmochronometer. The interesting thing happens if you have an astrophysical scenario that is akin to here, where you have a temperature that is low enough that the krypton stays in its separate states, but your neutron number density is high enough. So whatever you have formed in the isomer state or the metastable will beta decay into rubidium-85, but then anything that's formed in the ground state will neutron capture into krypton-86. So you get both pathways converging on the isotopic chain, which is pretty interesting.
Mm-hmm.
Pretty cool. Yeah, thank you for that. And if anyone out there is very interested in this kind of stuff, if you want to learn more about stellar evolution, you want to learn about programming and simulation and how all this stuff works, then join us. Come to the University of North Dakota. You can talk to all three of us if you like.
Yeah.
Hopefully in the same room next time.
Yeah. Well, we have both online courses and, of course, on-campus courses that students can take. We need a bigger room. That's what he's telling us.
We need a bigger room.
You heard it here, College of Science. Grant us the funds.
Yeah,
Right.
exactly. Anyways, thank you very much for doing this. We greatly appreciate it. And the other thing to note is our next podcast, a week from now, it will be on October the 14th. And we always leave you with a quote at the end. And fittingly, today's quote is by Hans Bethe, and it's an excerpt from his Nobel Prize lecture from December the 11th, 1967. And that Nobel Prize lecture is titled Energy Production in Stars.
Okay.
So here's the excerpt. Stars have a life cycle, much like animals. They get born, they grow, they go through a definite internal development, and finally they die to give back the material of which they are made so that new stars may live.
Nice.
Now, if you like this podcast, please remember to give us the thumbs up, smash that like button, subscribe if you haven't subscribed, and thank you very much for watching.
All right. Thank you, folks.
Thank you for having me.